TheWizBiz.com, and I'm still trying to make my ultimate Fisher Technique microcontroller.
Alrighty, so here we have our voltage and interface PCB from the last video. Please take a look at my last video if you don't know what I'm talking about. This PCB is built in this little cabinet here, and I've already powered it up. Let's see the back of the thing, as you can see here with the little connectors. Here we have our programming interface and our I2C, and these two power ports are now connected to 12 volt. So I'm not using the normal Fisher Technique rectifier yet. Let's see what it does on 12 volts. What I want is a reset button on the front, so this is going to be my reset button. That's very handy if you make program changes to the functions with a little lip switch here. Of course you want to have a opportunity to, or a possibility to reset the whole module without taking the power supply off. That would be very unhandy. Okay, so that's my reset button. Another new one on the front will be a trigger button that can mimic one of the 4 inputs that are now not in the shot. Let me go a little bit wider here so you can see my nice buttons that I have connected here. These represent your 4 inputs, by the way, and the little switches here, you can switch each input between a resistance characteristics or a voltage characteristic. So you can also use voltages as an input, but you can also connect an LDR or a NTC resistor or something like that, and you have to give it a small voltage, a small bias, a small preset with these little switches, and you can do that for each input individually. Okay, so on the output side there are 4 LEDs now on my breadboard. These, by the way, will not be on my Zauberling, I guess, because they're quite easy to make as an external module. And we have a few LEDs here on the outputs as well. I'm not sure if I'm gonna bring them to the front of the Zauberling. You can, as I said, easily make modules, external modules, to monitor your outputs and your motor outputs. Okay, so we have normally digital outputs, these for Q1, Q2, Q3 and Q4. These are on 9 volts levels, just to be backwards compatible with the normal Zauberlingen. So there are 4 drivers, transistor drivers in here. And what do we have more? Well, I have 2 potmeters, potentiometers. On the original prototype there was only 1 potentiometer, and now we have 2. I have 4 inputs, and as you can see, a nice feature of the display is that you can have little tags here which represent the function of each input for such specific functions like this. For instance, my first input is a power switch. So when I just push button 1, it's a power switch, and when I let go of it, the power is off. I also have a edge sensitive power switch, which is this one. You can just click it once and it's a toggle. So there is already some kind of flip-flop built in there. By the way, the trigger button can be overloaded in software for any of these 4 inputs, and I've now overloaded to edge. So if I use the trigger button on the front, you can see it has the same function as my inputs do. It switches on and off the motors. Motors are driven by the motor driver, and as you can see, I've made a small demonstration setup. You can see the direction and the level on these little LEDs on the output. These are 2 color LEDs, red and green. So this one is going like so, and this one's going like so. So you can see if it's driving a motor in clockwise or counterclockwise direction. And we can change that with dir 1. This is the motor direction of the first motor. So let's push this button and see what happens over there. And as you can see, it goes the other way around. So that is working, and the same for this button for the second motor. And look at the LEDs on the back. As you can see, if I push both motors are going in the other direction. Of course, I've made the potentiometers available for the speed, so I can control the speed, just like so. Okay, and for instance, we can take a look at a normal digital port. Just reset this to another function, give it a reset, and you're done. Now this program is called the Two Input Nands. So I have two Nands here. These are the inputs represented, and these are the outputs. If I push one button, nothing happens. If I do the second input of the NAND gate, nothing happens. But when I push both, you can see that the NAND is giving its other output. Alright, so let's do the flip-flop demo. Okay, so here we have the SR flip-flop. This is a set and reset flip-flop with a clock. So 1 will be the set and 3 will be the reset, and the clock just toggles between and makes it a toggle or a T flip-flop, just like so.
Alright, enough flippy floppies, and let's go to the mono flop, another flop. There it is. Potentiometer 1 is the input sensibility, and potentiometer 2, we can use that for the length of the pulse. And there it goes. And this clearly demonstrates the fun of having a display on your microcontroller, isn't it? Okay, that's enough for experimental breadboards. Let's fast forward to a readily designed PCB that I made, and that came after a few weeks of waiting and anticipation. As you can see clearly on one side, the SMD components, the transistors that drive the outputs. So we have four outputs already assembled there, and under the dip switch in a moment, I'll show you, there are also components. These are the 4 diodes that are necessary to make the trigger button function. And ready to solder on our SMD buttons for reset and triggering, and the logic switch. Potentiometers at the bottom over here, and one through-hole component going there, that's the OLED display. And hey presto, here's one I prepared earlier. Well, one side of it, as you can see, everything's been soldered on SMT islands, or it is through hole like the display or the potentiometers. Sides of the potentiometers were clipped, so they were soldered on the front, and the pins going through the bottom. And there we see our region for the motor driver to be soldered on, and a region over there for the microprocessor. Of course, I'm aware both components are readily available as SMT components, but by mounting these piggyback boards, it gives you an extra layer of copper routing. So I thought I'll give it a try. Just solder some pins and some headers to the islands. Clip off the top of these long headers, and you can quite easily slide on the boards on their poles or on their mounting spot like this. Of course, you have to solder it very quickly because the wires are very short. But in this way, well, it was quite easy to make that extra layer on my PCB. So you might speed up your soldering a little bit, but I think it's a nice way to piggyback mount a board like that. Finally soldered the edge connectors, the header connectors on. That's going to connect to the interface and power board. So these are on exact the same spots on the PCB, of course. There they go. And it snaps on nicely. And there you have it, your multi-layer sandwich board that makes great use of the height of the tiny space within these cases. It just snaps into place, and voila! And here we have it, ready to be finally covered with our nice laser printed and laminated front. I just received even better material that didn't make it to this video, and just slide on the vintage Fisher Technique rectifier module, put on the clip, and there we have it. We are in business with a 2 input NAND, 2 of them. Just like so. Okay, here we have the output indicators that I introduced in a moment ago, so that gives you a more clearer view on what's going on the outputs. You see it reflects the display quite nice. Let's plug in the other one as well, the 2 color LEDs that give some indication about speed and working direction of the motors that you could connect to the motor outputs. Yeah, going from red to green. So we're all ready for a digital test of a few of these Zauberlingen. You see the three flip-flops on the bottom. They are looped through, making a 3-bit binary counter in that way. That's been fed into a binary decoder, a 3-bit decoder, and another one. First decoder will take care of the first 4 LEDs, and the other decoder will take care of the LED 5, 6, 7 and 8. So by pushing the button, it all steps 1 bit further. It counts 1 bit further in a binary way that's been decoded here at the top by the 2 binary decoders. Well, more or less this is just a proof of concept, because why should you use 5 Arduino microcontrollers just to make a 3-bit counter that you immediately decode again? But hey, it's just proof of concept, guys. I'm just hoping you're more impressed with my nunchuck. You know that nunchuck? We have a I2C bus on here, so this is really something a Zauberling can't do and a Zauberling can, because with this I2C bus it's quite easy to make a nunchuck controller. As you can see, I can control both motor outputs with my nunchuck, and you could also get the gyroscope and button data in there. So the I2C bus, which offers a lot of sensors to be connected, like these, can be a real bonus. So let's quickly try this TCS3472 color sensor in my little setup over here. Can be connected directly to the Zauberling on the back on the I2C or the I2C bus over here. There it goes, a little light goes on, and if we give the Zauberling a reset, it should recognize the sensor, and the sensor is able to recognize a red activating output 1 or green activating output 2 on the Zauberling. Here we have blue, that should light up the LED on output 3, and finally yellow can also be detected. So in essence you have everything to make a nice color separator. Well, that concludes my video. It concludes my series of 2 videos. You see the interface and power PCB connects to the Zauberling main PCB, producing a backwards compatible companion for your Fisher Technique traditional vintage Zauberlingen. If you liked this video so far, or it was in some way entertaining or useful to you, please give it a thumbs up. I hope to see you with my next video. See you soon and happy hacking!